Meeting the goals of hydrogen purity is rarely as simple as dropping a filter into the line. If you choose an opening size that is too large, you miss fine contaminants slipping through, catalyst fouling, valve wear, and sensor drift. And if you choose an opening that is too small, you introduce unnecessary pressure drop, starve downstream equipment, and drive up energy costs. Striking the right balance between capture efficiency and flow is the core challenge when specifying mesh opening size. A better path is a deliberate sizing approach that links opening size to your particle size distribution, target flow, and allowable pressure drop. By pairing the correct mesh count and aperture with suitable wire diameter and weave, you can capture the particles that matter while keeping gas moving efficiently. When engineered and validated with representative samples, the right opening size delivers cleaner hydrogen without sacrificing throughput. So when hydrogen is used in applications like fuel cells, chemical processing, or energy storage, even trace levels of particulate contamination can disrupt performance. Tiny particles can damage sensitive catalysts, clog flow channels, or compromise downstream components. The mesh opening size in a filter directly determines what particles are captured and what particles continue into the system, making it one of the most important specifications in filtration design. If the opening size is too large, contaminants that appear insignificant in bulk processes may still cause problems in hydrogen systems. Conversely, an opening size that is too small can overly restrict flow, increase pressure drop, and reduce system efficiency. The result is wasted energy and higher operation costs, without always delivering better cleanliness. Finding the right mesh opening size means striking the balance between protection and performance. The geometry of the mesh also plays a role. A square mesh opening can provide consistent, predictable capture of particles, while alternative weaves may change the retention profile. Additionally, wire diameter influences the strength and open area of the filter, both of which impact how long the mesh performs before needing maintenance or replacement. These physical details are just as critical as the numeric size rating. So ultimately, selecting the proper mesh opening size ensures reliable hydrogen purity, maintains smooth flow, and extends equipment life. It is the foundation of which the rest of the filtration system operates, influencing everything from energy consumption to long-term reliability. That's why engineers place so much emphasis on designing the correct mesh opening size so early on in the process. Choosing the right mesh size for hydrogen filtration is all about the balance between all the parts in the process. The optimal opening size depends heavily on the application, the system design, and the contaminants most likely to be present. Engineers must weigh multiple variables to ensure they achieve the right balance between purity and efficiency. One of the most critical factors is the required hydrogen purity level. Applications demand extremely fine filtration, since even microscopic particles can poison the catalyst layer. In contrast, industrial processes with less downstream components may tolerate slightly larger mesh openings without compromising performance. Operating conditions can also shape the decision. Systems running at high pressure and flow rates require a mesh that can withstand mechanical stress while maintaining a stable opening size. Likewise, temperature variations or exposure to reactive chemicals may call for specialized alloys or coatings, which can influence both wire diameter and effective mesh size. And finally, maintenance intervals and total cost of ownership play a role. While finer meshes may offer higher protection, they also clog more quickly and require more frequent cleaning or replacement. By carefully evaluating the purity requirements, operating conditions, and maintenance strategy together, engineers can select an opening size that aligns with both technical performance and operational efficiency. So when selecting mesh opening sizes for hydrogen filtration, one of the biggest challenges is balancing filtration flow rate with efficiency. A finer mesh can capture more contaminants, but it also restricts gas flow, increasing pressure drop across the system. If the mesh is too fine, the filter may cause bottlenecks, reduce efficiency, or require more frequent maintenance to prevent clogging. And on the other hand, larger mesh openings allow for higher flow rates with lower resistance, but this comes at the cost of reduced particle capture. In applications where hydrogen must meet strict purity standards, such as fuel and cells, oversized mesh may allow harmful particles to pass through and damage sensitive downstream components. The key lies in identifying an optimal middle ground. Engineers often use computational modeling and real-world testing to measure how different mesh sizes impact particle retention and pressure drop. By simulating performance under operational conditions, they can select a mesh size that maximizes efficiency without compromising flow. In practice, this balance often means designing filters with layered meshes, combining a fine filtration layer with a coarser support structure. This configuration helps capture contaminants while maintaining mechanical strength and minimizing excessive pressure loss, ensuring the system remains stable over time. Thanks so much for watching. If you have any questions, click our Talk to Us button to get in contact with our many experts on woven wire mesh. And if you'd like to learn more about woven wire mesh or our many products, we have a learning center filled with written and video content to make you an expert. We also have a YouTube channel. And don't forget to click that subscribe button and ring that bell to keep up with all things WS Tyler. Once again, my name is Andrew Kotlar, and I'll see you around in the next video. Bye for now.